Today we're going to learn about Markov chains, which are a beautiful branch of probability, which also have really powerful applications in algorithms. A Markov chain is, well, let me start by giving you a Markov chain is a very powerful tool for modeling systems that evolve over time. And there are many systems where you can sort of describe that evolution from the current state. Here is what can happen next. And there may be some randomness involved in that what can happen next, right? The weather is a good example of this. It has a lot of applications in modeling. If you want to understand these systems and simulate them, you will be running a Markov chain. So they can be used to model nature. We can also create artificial Markov chains to explore and sample from complex state spaces. And you can do a whole class on Markov chains. We're going to do 2 lectures because that's what we have time for, but it'll hopefully give you a taste and you'll discover how amazing they are. I'm going to introduce them by showing you a really cute algorithm for 2SAT. We've talked about satisfiability. We talked about DNF counting algorithms, right? So 2SAT is where you have a 2CNF formula, right? Where you have an AND of ORs. But you only have 2 variables per clause. And so, as you might guess, 2CNF is polynomial time solvable. You might guess this because we always talk about 3CNF being NP-hard and we never talk about 2CNF being NP-hard, right? So it is polynomial time solvable. There are a number of different algorithms for it, but I'm going to show you what I think is the cutest one. Okay. So the algorithm is start with any assignment. Now, while the formula is not satisfied, we are going to try to fix it. Okay? So if the formula is not satisfied, why is it not satisfied? Yes? Right. Some clause has both terms, or both terms, false, right? It has a variable in it that it has a non-negative variable in it that's set to false, and a negative variable in it that's set to true, or something like that. Okay, so we have this clause, and both of its variables are set to false. Now, if this clause is in fact satisfiable, then that means that the assignment we have is not that appropriate satisfying assignment. It is wrong, right? The correct satisfying assignment cannot set these 2 terms, these 2 variables, the way they are currently set, because that would make this clause, that makes this clause false. So at least one of these 2 variables is set wrong. So we should flip that one to the other value, right? That would make our assignment more correct, closer to the valid assignment, right? The only problem is we don't know which of the 2 variables is wrong, right? Maybe one of them is set correctly. If we flip that one, we're actually becoming less like the correct assignment. Okay, so there are two possibilities. We don't know which one. What should we do? Yes? Exactly. Flip one of its two variables at random. Okay. So this is a small local change to the variable settings, right? This is the whole algorithm. The question is, does it work? How well does it work? So I'm going to give you a nice proof that this algorithm actually finds the satisfying assignment in expected polynomial time. Okay. For this analysis, I'm going to fix a satisfying assignment and I'm going to measure my distance from it in terms of the number of variables that match S. I guess it's an inverse distance, right? We want all the variables to match. If all of the variables in our assignment match the satisfying assignment, then we have found the satisfying assignment. Okay. Now, let me write f of k be the expected time to reach assignment S if currently k variables match. Okay. This is a well-defined quantity. Everybody understand what it is, right? Yes?
So take all possibilities of k variables matching?
No, I'm actually, this is going to be, I guess I would say the worst case expected time over all possible ways that you could have k matching variables. Okay. It actually turns out that no matter which k variables are matching, it's the same. So it doesn't actually matter. But yeah, this is sort of technically more correct. Okay. So this is a well-defined quantity. How can I relate these various quantities so that I can solve them? Well, first of all, if I have n matching variables, then of course the expected time to get a match is 0. Right? What if I have 0 matching variables? Well, I'm going to flip one of them, and that's going to make a match. So I'm going to end up in a state with one matching variable, right? And that took me one flip. So this is 1 plus f of 1. Yes?
What if you have 0 matching variables, but it's already a satisfying assignment?
Good. So I was going to mention this at the end, but I am doing this analysis in terms of when do we hit S. And I'm going to show a worst case expected bound. This assumes that we didn't hit some other satisfying assignment first. Okay? So there may be other satisfying assignments, and I may hit them before I hit S, but that just means I finish sooner. So if I just bound the time to hit S, I'm upper bounding the time to find any satisfying assignment. Yes? Okay. So f of 0 is 1 plus f of 1. But what can I say more generally? suppose that I currently have k matching variables. What can happen? Yeah?
I guess half the time you'll end up with k minus 1, and half the time you'll end up with k plus 1.
Yeah, that's kind of the worst case scenario, right? Which is what we want to bound, right? There are one cases where both of the variables are wrong. Yes, in which case it doesn't matter which one I flip, right? But in the worst case, one of the variables is wrong and one of the variables is right. So I can say that the time that it takes from k is, well, half the time I'm going to flip the correct variable and end up one step closer. And half the time I'm going to flip the incorrect variable and end up one step farther away. Thank you. There's the actual flip that I did. Yes? So now I have, I believe, n equations, or n plus 1 equations defining n plus 1 values for f. So I can solve this. Okay, it's just a big linear system, right? First of all, in order to compute the upper bound, I'm going to put equality here, right? And now what I'm computing is an upper bound on the actual time. Okay. So what I do, I rewrite. I say that f of 0 minus f of 1 is equal to 1. And looking at this formula, I double, do the obvious things. F of k minus f of k plus 1 is equal to 2 plus f of k minus 1 minus f of k, right? So I multiply this formula by 2. I have 2 f of k's over here, right? I have an f of k plus 1 and an f of k minus 1 over here. So I move the f of k plus 1 over, I move one of the f of k's over, and I have this formula. Yes? Okay, but now notice that all of my expressions are in terms of a difference, right? So I can write g of k as f of k minus f of k plus 1, right? And now what I have is that g of 0 equals 1, and g of k is equal to 2 plus g of k minus 1. Yes? And so that's a nice simple recurrence, right? The g's go 1, 3, 5, 7, 9, right? G of k is equal to 2k plus 1. Right? And that is f of k minus f of k plus 1. So f of k plus 1 is equal to f of k plus 2k plus 1. In other words, f of k is just a sum of odd integers, right? Which is squares, right? Right? I see some skeptical faces. Anybody want to ask a question? Yeah, go ahead. F of n is, oh, sorry, did I invert between 0 and n? Let's see. Yeah, you're right. I should be doing it in terms of differences rather than matches, right? I should have f of 0 equals 0 and f of n equals 1 plus f of n minus 1. Yes?
If there's like a clause that such that the clause is, think about it. Sorry.
Yeah, remember, we're assuming the worst case is where there's one matching and one non-matching variable in an unsatisfied clause. Because then we have a 50-50 chance of doing the right thing or the wrong thing. If both variables are not matching, then we are guaranteed to do the right thing.
Like, how do you like, do you need to like tell change the analysis to like account for that?
The change was that when I originally wrote this formula, I stated it as an upper bound, right? Because the upper bound is true whether you're in good shape or in bad shape, whether you're in the good case or the bad case, right? So by turning that into an equality, now I'm not computing an arbitrary expectation. I'm computing an upper bound, which is the worst case possible expectation. Yes? All right. You know, this is one of these bugs which has survived in my notes for 20 years, but I'll go fix it after lecture in terms of the n versus 0. But it's symmetric, right? And that's actually what we're doing here. We can forget about the underlying problem. We essentially have a counter running back and forth on the number line with a 50-50 chance of moving right or left in each step. And we are asking, how long does it take to reach one end or the other of the number line? Right? This is what is known as an unbiased random walk. On the line. Okay. And this is perhaps the simplest, or one of the simplest, Markov chains. Right? Each step is, each state is determined from the previous state. And what's critical about Markov chains, what makes them tractable and interesting, is that the past history doesn't matter, right? It doesn't matter how you got to this point. In the next step, you are going to get to one of the two neighboring points, and the probabilities are not affected by your history. Okay? And that is the sort of fundamental feature of Markov chains. The rest of, I won't even bother writing down the rest of this, of the analysis, right? We know how to do this. We now have an algorithm that runs, that has an expected runtime of n squared to get to the end. So if we run for 2n squared time, we have a 50-50 chance of reaching the end. So we have an algorithm that has a 50% success probability. And if we do that log n times, which just means running the algorithm log n times as long, then we get a high probability of finding the satisfying assignment. Yes? Are you trying to get me to answer the homework question for you?
Wait, I didn't see the reset.
Aha! Well, maybe that's worth a look. This algorithm can actually be generalized to 3-sat, and it doesn't give you a polynomial time algorithm, but it does give you the very best known algorithm for 3-sat. Just this simple idea of flipping a variable in an unsatisfied clause. And it took decades before people noticed that. But it's a lovely, simple algorithm. Okay, so more generally, a Markov chain first of all, a state space, set of states. Okay. Which I can call SI. Okay. And a set of transition probabilities. Which is Pij is this the probability that your next state is Sj, given that your current state is Si. And this allows you to now talk about generating a sequence of states, x0, x1, x2, and so on, according to these transition probabilities. So the outcome of a Markov chain, or a sample from a Markov chain, is a sequence, a possibly infinite sequence of states. Okay. What is key is that the probability that xt is equal to some state S, conditioned on all of the past, is that you can ignore everything except the immediately previous state. Which is why the transition probabilities are enough to specify everything that happens, right? The Markov chain also keeps things simple. This is what is known as the memorylessness property. Because it doesn't remember how it got to state t minus 1. It's just going to go to the next state regardless. You could imagine a sort of more general version of this where the transition probabilities change from time to time, and that could still be memoryless, but it would be much more complicated to analyze. Right? Here, the transition probabilities are fixed over all time. Okay. Obviously, the sum over j of the PIJs is equal to 1 if these are meaningful transition probabilities, because you have a probability, because you have to have a probability distribution on what the next state is going to be. Okay. I haven't bothered. You can also have different ways of choosing. This does not specify how x0 is chosen. And depending on the application, you might say that x0 is a particular state, it is an arbitrary state, it is a probability distribution over states. It doesn't actually matter, because one of the really interesting things that we are going to show about Markov chains is that their long-term behavior is kind of independent of the starting state. Right? It's the memorylessness property again, that the ultimate outcome doesn't remember where you started, so it's not really affected by it. So I've got these PIJs. Notice that I now have a matrix P from these PIJs, right? Which is called the transition matrix, right? Now, suppose that Q is the vector probability distribution for xt. What is the vector for xt plus 1? Yeah? Exactly. Except that the way I've written it down, you have to put it on the right side, right? Because the way that you get to state j in time t plus 1 is that you are in some state I before with probability qi, and then you transition to j with probability pij, right? So p prime j is equal to sum over I of qi pij. Or sorry, q prime j. And by induction, the state at time t is just Q times P raised to the T power. Sorry, this is Q0, your initial probability distribution, times P raised to the T power. So there's a simple linear algebraic description of the probability distributions, which we are not going to pay any attention to because I don't like algebra. We're going to take a different perspective on it. But do people understand the general perspective? Okay. So let me tell you my preferred mental model for Markov chains, which is that they are a graph, not a matrix. So given a Markov chain, you can make a graph of the Markov chain. It is a directed graph, and there is an edge, ij, if pij is not equal to 0. Okay. So this is very natural. It's basically saying I'm not interested in the exact details of the numbers. I'm just interested in where are the non-zeros in the matrix, right? Where are transitions possible? I'm not going to worry about how probable they are, but just that there is some possibility of a transition from I to J. Okay? And this is useful for thinking about the evolution of the Markov chain. So, of course, we give the edge weight Pij, which means that every out degree in this graph is 1. And possible state sequences are just paths in the graph, right? In order to transition from states from I to J, there has to be a non-zero transition probability, which means there has to be an edge. So if you can have a particular sequence of states, it means that there is a path through the graph. Okay? Now, the most important concept or result for Markov chains has to do with what's called a stationary distribution. A stationary distribution is a distribution pi, such that pi, p, is equal to pi. Okay. This is saying that if you were in the stationary distribution at a certain time, then in the next time step, you will still be in the stationary distribution. Okay. Now notice this is a stationary distribution. It is not a stationary state. We are not saying that if you're in this state now, you stay in that state next, right? You're probably going to end up in a different state, but the distribution of states that you're in is stationary, right? And of course, if you condition on which state you're in the previous time step, that conditioning makes you not stationary, and so you won't be in the stationary distribution in the next step. But if you have no conditioning, right, if you just know that you're in the stationary distribution, then you're going to stay there. Okay? And for those of you who had the linear algebra, this is an eigenvector with eigenvalue 1. Okay. And the stationary distribution sort of represents the steady state behavior of the chain, right? It's like it's a stable point. If you end up in the stationary distribution, you're just going to stay there forever, right? Until, this is very quantum, right? If you observe the chain, then the distribution collapses and you're not in the stationary distribution anymore. You're in the state that you see, okay? But it stays there as long as you don't look. And another thing that I'm going to sketch out is that if you run the chain long enough, it converges to this stationary distribution. Doesn't matter what the starting conditions are. Modulo some technical conditions, which I'm going to go through. Okay, so lots of Markov chains have these stationary distributions, and they are very useful when they exist. But in order to say which, we need some definitions. We basically have to rule out some weird edge cases that prevent a Markov chain from having a stationary distribution. Okay. So just to give you a chance to think about this a little bit, forget about the numbers involved. Can you think of a graph shape that for some reason might not have a stationary distribution? Yes?
One vertex here, no edges.
Great. So one possibility is, well, let's say what we need to rule out. So one thing we want to rule out is disconnected graph. Now, this actually can have a stationary distribution, right? So, but this is still a problematic example. Okay. This graph does have a stationary distribution like 1/2, 1/2, but it also has a station distribution like 0, 1. And it also has a 1/4, 3/4. And it also has 1, 0. Right? So this is a graph that has many stationary distributions. And that's bad. I mean, sorry, it's not bad, but it's a case we'd like to rule out. All right? What are some other examples of graphs that, again, they might have stationary distributions, but they're weird in some way? Yes? Great. So this graph has no stationary distribution, right? So this has multiple stationary distributions. This has none. Okay. Right? You can't put any probability on any vertex, right? Because it's just not going to stay there. Right? There's one other case that's weird. Again, it doesn't rule out a stationary distribution, but consider this little 2-cycle. Right? What's the state space evolution going to be if you start in the top state? Well, you're just going to alternate back and forth between the top and the bottom, which means that, you know, on even days you'll be in the top in the bottom state, and on odd days you'll be in the top state. And so neither of these is really the stationary distribution because it keeps flipping, and it never changes from that. You don't converge to, right? This has a stationary distribution, right? If you just say 50-50, right? But this periodic alternation will never converge to that sort of 50-50 alternation. And so these are the 3 kind of bad situations that get in the way of the fundamental theorem of Markov chains, which I'm about to show you. Yes? Yes, a longer cycle, exactly. But it's the same problem, which is periodicity. Okay. So we're going to make up some definitions to rule out these possibilities. Okay. First of all, we're going to talk about irreducibility. Okay. The irreducibility just means that there is a path between any 2 states. Okay. And that rules out already 2 of our bad examples, right? It guarantees that, right? It means that you can't have this infinite directed line because you can never get back. And you also can't have the 2 disconnected vertices, okay? So this essentially corresponds to strong connectivity, right? In the directed graph of the Markov chain. The next definitions are terms persistence and transience. Let's define these basic random variables, or these basic probabilities. Rijt is equal to the probability that starting at I, the first encounter with J is at time t. So if you sum over all t, you should get 1. Okay. We can then define Fij as the, sorry, it's not the case that Rijt is always equal to 1. Fijt is the probability that you ever reach J from I. And finally, we have what's called the hitting time, Hij, which is equal to the sum of t times Rij of t. So in expectation, how long will it take for you to get to from I to j? And now with these definitions, we say if Fii is less than 1, we say I is transient. Otherwise, we say it's persistent. Okay. So persistence of a state means that if you're on that state, you know that you'll get back to it eventually. Right? Now, if Fii is less than 1, then the hitting time is infinite because there's a chance you'll never come back. The converse might not be true. Okay. If Fii equals 1, but Hii is infinite, this is a weird case that only mathematicians care about. This is called null persistent. Right? You will eventually get back, but it will take infinite time. Okay. Now let's relate this to the graph. Okay. A graph has strongly connected components. Okay. Some of them are final strongly connected components, which means they have no outgoing edges. Okay. Yes? Well, you need infinite state spaces in order to make that happen, right? And I think if you can start with the line and create a set of transition probabilities back to the 0 state from all of the states on the line, that gives you, that sort of, shrinks so that your expected time to get back is 0. So actually, the unbiased random walk that we looked at, we showed that there's a finite time to get back to your state. What was that? In the one-dimensional case, yes. No, I don't think so, because, right, when you leave your state, you can talk about the expected time to... let me hold that. I'm not sure. I don't want to say something wrong, so I won't say anything. Okay, so when you have a graph and you sort of mark out its connected components and draw circles around them, what you end up with is, in general, a DAG on the connected components. Right? And you can imagine walking through the DAG, and some of these connected components don't have any outgoing edges. which makes them final, right? If you traverse a path and you end up in one of these strongly connected components, you can't leave, right? A non-final component has a positive probability of exiting after n steps, right? Because if you have a non-final component, there is some path in that non-final component, and that path that leads to a different component, right? And there's a non-zero probability that you will take that path. So there is a non-zero probability when you're on this vertex that you will leave the component. Of course, once you leave, you can't come back. So that means that these are all transient. Right? So vertices in non-final components are transient, but vertices in final components, for pretty much the same reason, are persistent. Okay? If you're in a final component and you're on some vertex and you're trying to get back to some other vertex, well, it's a strongly connected component, so there is a path to your destination vertex. So there is a fixed probability that you will get to that vertex in some number of steps. Right? If you fail, you'll be at a different vertex, which also has a fixed probability of getting to your target after some number of steps. So you can, again, imagine taking repeated attempts to get to the target vertex, and you have some finite probability of doing it each time. So with probability 1, you will do it, and your expected time to do it is finite. Yes? Because it's I'm talking about finite graphs here, okay? Yeah, that's, again, computer scientists, so I don't like to think about infinities. Okay, so final means that you are non-null persistent. Okay. And so what we can conclude here is that basically in a finite Markov chain, there are no null persistent states, and you can tell whether they're transient or persistent just by whether you're in a final component. Okay. Now let's talk about periodicity. This is another thing. This is the other thing that we were concerned about. Okay, so periodicity of a state is the maximum value t such that the state only has non-zero probability at times a plus big T times I for some integers a and I. Right? So a state is periodic if you can only get there at time steps 4, 7, 10, 13, and so forth. Right? There's an initial offset and then just a sort of repeating period with which you can return to the state. Okay. And we say that a chain is periodic if some state has periodicity greater than 1. Okay. And we saw an example of that, right? A cycle of length t has periodic states. Yes? Well, what is so you've given me a line, but you haven't defined the walk on the line.
Just like directed line, you can only go to the right.
Um,
And maybe the last one's like to itself.
well, if it's an infinite line, then it.
Finite.
Oh, a finite line. then so periodicity is only really interesting for persistent states, right? Transient states are uninteresting anyway. Okay. So a cycle of length t, of course, has periodic states. All of them have period t. But more generally, in order for you to have if I want to tell you that this vertex of the graph has period t, if you think about it, that means that every cycle involving this vertex has to have length a multiple of t, right? So a state having period t, for that to happen, every cycle containing the state must have length, which is a multiple of t. Okay. And so, again, talking about these basic examples, we saw that periodicity can be weird, right? If you start in state 1, you might only be back in state 1 every third step. And so what kind of stationary distribution can you talk about? Is state 1 part of it or not? Okay. Now, this fact makes it very easy to eliminate periodicity from a Markov chain. All you do is add self-loops. Which in Markov chain language is just saying you make a small probability of not transitioning. Okay? So this does not at all change the sort of the nature of the Markov chain or the path that you take. It just slows things down a little bit, right? And if you make the self-loop probability small, then it doesn't slow things down very much. We'll often just make it a half and make the Markov chain half as fast, right? But this eliminates any periodicity concerns because now there's a cycle. Now you can get to a vertex at any time because you can just keep going around the self-loop. Okay, just to complete our dictionary, we say state is ergodic if it is aperiodic and non-null persistent. And we say that a Markov chain is ergodic if all of its states are. And what that means is, we've sort of covered all the cases now. If you have an ergodic chain, it means that sufficiently far in the future, you could be in any state. Right? Each state of this Markov chain is one that, modulo some startup time, you could always get there at some point in the future. Okay. So now, with all these definitions, I can give you the fundamental theorem of Markov chains. Any irreducible, finite, aperiodic Markov chain has or satisfies first that all the states are ergodic. Next, that there is a unique stationary distribution. Pi. Also, all the FIIs equals 1. That just means there are no transient states. Also, the return time, right? The hitting time to return to I from I is just 1 over the stationary probability of being in state I. And finally, the number of visits to state I in t steps approaches t pi I as t goes to infinity. So a lot of these are kind of, your intuition says they have to be true. Again, we've ruled out periodicity and disconnection and so on and so forth. The real important, difficult statement is that there is a stationary distribution and that it is unique, right? Given that you know there is a stationary distribution, the fact that the chain is irreducible, which means that you can always get back to a state with some constant probability, that tells you that Fii is equal to 1, right? It also makes intuitive sense that if you're going to be in state I, pi I of the time, then the interval between occurrences of state I is going to need to be 1 over pi I. Yes? And then this is not actually trivial. You use something called renewal theory to argue that that follows, right? And again, this also this is kind of a like a central limit theorem for Markov chains, basically, or a strong law for Markov chains. Okay, so I'm not going to take the time to prove this because I want to spend time showing you algorithms. It's actually not that hard to prove. It's about showing that there exists an eigenvector with eigenvalue 1 and showing that there's only one of them. If there are multiple ones, that tells you that the graph is reducible, right? You get multiple eigenvectors if the graph is disconnected, and one eigenvector identifies each component. Okay? So now we've got our background on Markov chains. In the rest of the lecture, I will make use of it to do some interesting things, but let's take a break first. Many of them are very easy, though. No, they really are. Like, we're just getting started with Markov chains, so I couldn't ask you the hard stuff yet.
How many of the questions on Markov?
I don't know, 3 maybe, 4. I can't remember. I'm kind of memoryless myself. Yes. No, it was published on Wednesday night, but it takes time for these things to be put. I get them into NB, but sometimes the website is late to link to them. Okay, so for our first interesting application of Markov chains, I want to talk about graph connectivity. This is one of the most basic algorithmic problems, right? You're given a graph, you want to know if it's connected. In your elementary algorithms class, you learn depth first search, breadth first search. These are all ways to determine if the graph is connected. And these are great. They run in linear time. So what else could there be possible to say about graph connectivity? Well, time is not the only resource that computer scientists are interested in. And graph connectivity is very interesting when you think about space-bounded computation. Okay. How much RAM do you need in order to decide if a graph is connected? Okay. We've seen space-bounded computation before, although it was a recorded lecture, right? If you think back, there was this lecture on streaming algorithms, which asked you to estimate and count things using only a logarithmic amount of space, right? So this question is in the same category, right? What is the space complexity, not the time complexity, but the space complexity of determining whether a graph is connected? Okay. Now the graph itself, of course, is linear size because it defines the size of the problem. But we assume that it is available as a read-only artifact. And the question is, how much writable memory do you need to maintain the state of your algorithm as you are checking connectivity? So how much space is used by breadth first search or depth first search? Yeah. Exactly. So BFS or DFS use it depends how you count it, right? And you either need use n space. So we can get very nitpicky about exactly how we represent the graph and so forth, right? If we think that the vertices are integers, right? And so the graph is represented as a collection of integer pairs describing edges, then you can use a bit array, right, to determine which vertices you've seen. And so it's going to be n space. For certain other representations, you might need to use a machine word to get the labels of the vertices that you've seen. But we'll look at this one. Is that optimal? Turns out that this is very far from optimal. There's a beautiful result from long ago due to Savage, which I'm going to show you because it's beautiful, but not because it's randomized. It's a very simple algorithm. We'll call it check connectivity of G. Let's say vertex V. We want to check if you can get from vertex V to vertex W. But we're going to add a third parameter, which is a distance. Okay. Can you get from vertex V to W on a path of distance D? Okay. And the way that you check this is for all vertices, X, you say yes if you can find a path from V to X, and you can find a path from X to W, then you return yes. Otherwise, if you fall out of the loop, you return no. So this is Savage's algorithm for testing connectivity, right? And it's clearly correct because if there's a path of length D between V and W, then there's some vertex at the midpoint. And so you just find that vertex and recurse. Yes? Yeah? Oh, yes, thank you. That's exactly the point, is that since you're speculating about a midpoint, the length of the path there is only D over 2 instead of D. Right? So then, right, this is your sort of your inner routine, and then what you do is for all pairs, for all W, you call check connectivity from V to W, and you aggregate, right? So if V can reach everything, then the graph is connected, and this is how you can check if V can reach a particular vertex. So what is the space requirement for this algorithm? Exactly. We're making 2 recursive calls, but we only need to remember one of them at a time, right? So the space for working on paths of length n, well, you need log n bits to remember where you are in your loop. And then you need the space to make a recursive call on looking for paths of length n over 2, right? So you have log n layers of recursion. The top half of those layers each requires about log n bits. So you end up with an order log squared n space for connectivity. Okay. Now I'll mention Savage's algorithm works equally well for directed or for undirected graphs. Okay. But if we home in on undirected graphs, we can do better. So suppose that you were just dropped into the Minotaur's maze and you want to get out. And you don't have anything to take records with or anything. What strategy might get you out of the maze? Hopefully I've queued up a good idea by ordering the lecture this way. Yeah? Random walks, right? So a big achievement for this sort of connectivity work was thinking about random walks on undirected graphs. Okay. If you think of, the exit to the maze as one more vertex, right? Then the question becomes a question of just how long does it take you to reach a particular vertex if you take a random walk through a graph, right? So this, of course, is the obvious Markov chain, right? Each step, you choose a random neighbor as your next step. Okay. So what this means is that the probability of transitioning from U to V is just 1 over the degree of U, right? And if we pull out the fundamental theorem, right, we can say that we can exhibit a stationary distribution where I'm just going to set pi sub v equal to the degree of v divided by 2m. And I claim that this is a stationary distribution. Yes? So what I am giving you here is a stationary distribution. And periodicity doesn't stop you from having a stationary distribution. It just stops you from having a unique stationary distribution, right? Yeah, so that answers your question, I think. So my claim is that this is stationary, right? To check this, right, the probability that you end up in state U is equal to the sum over neighbors of U, right, of the probability of the stationary probability that you're in that neighbor times the probability that you transition, right, which would be PVU. The probability that you're in V is just d of V over 2m. What is the probability that you transition from V to U? Well, it's 1 over d of V. So the d of v's cancel, and you end up with your d of u neighbors each contributing 1 over 2m, so you end up with a stationary distribution. Okay? Now, as was just pointed out, right, the fundamental theorem, so I mean, we show there is a stationary distribution. The fundamental theorem says that it is unique if we satisfy the right conditions, right? In particular, if the graph is a connected graph, which is what we're trying to test, then the stationary distribution is unique. But on top of that, we also need to get rid of periodicity, which, as I said, we can do by adding loops, which just mean you take certain times you don't move, right? And that makes your graph aperiodic. Also, because it's an undirected graph, it is strongly connected, right? So we don't have to worry about transients. So we can add self-loops and apply the fundamental theorem. And that lets us conclude that the hitting time, HUV, is equal to, HVV, the return time to vertex V, is just 1 over pi V, which is equal to 2m divided by d of the degree of V. And that's almost what we want, right? This is already telling us that if you start at a vertex, it's only going to take you polynomial time to return to that vertex. But that's not what we're interested in, right? What we're really interested in is how long will it take you to get from vertex V to a different vertex, U, right? And so for that, we have the more general hitting time, right? We're interested in HUV, the time to reach V from U. And we're also going to define a commute time, which is just the time to go to work and come home again, right? To go from a vertex V to U and then back to V. Okay. We are also going to define the cover time from U, which is just the time to reach all the other vertices starting from U. And finally, the overall cover time is the worst case cover time from any vertex. Okay. So the cover time is the expected time to visit the entire graph. Now I'm going to prove to you that the cover time is polynomial. So you only need to wander randomly for a polynomial amount of time in order to encounter all of the vertices of a graph. And a fortiori, you only need to wander a polynomial amount of time in order to encounter a particular vertex of the graph. Right? What does that suggest about an algorithm for testing the connectivity of a graph? How much space do we need? Yeah? How come? What do we need to remember?
You can do it like for each vertex in order, you check whether it's reachable, and then you just keep trying to go to that vertex until you reach it, or the number of steps you've taken is more than a point
And so what do you need to remember?
Just your current vertex and the number of steps you've taken.
And where you're trying to get to, right? So to test connectivity, we just try to reach all vertices. And this requires us to remember the target, the current location, and the number of steps that we have taken, right? And we run for a number of steps which is twice the worst case hitting time, which is upper bounded by the cover time, right? And so if we run for twice the cover time, then we can declare failure if we haven't seen this vertex, right? Okay. So what is that cover time? Let's look at a couple of examples because it's it's kind of fun. So we've already actually analyzed one cover time. What's the cover time for the line? Already forgotten start of lecture? Yeah? It's n squared, right? That's what that was the 2-sat example, was essentially the cover time of the line, right? What about a clique on n vertices? What does it mean to cover a clique? Visit all the vertices of a clique. Yes? Exactly, right? You go to a random vertex each time, so coupon collector, right? So this is order n log n. Great, we're on a roll. Let's attach the line to a clique. This graph is called, I have to turn sideways, but this is the lollipop graph. Graph theorists have so much fun because I get to name all of the graphs. What's the cover time on a lollipop? Is it like, you know, one piece of it is n squared, the other piece of it is n log n. So what's going to happen? Is it going to be just the worst case, that it's sort of the n squared time that it takes to cover the line? So this is actually quite surprising. This one is theta of n cubed. Okay. If you think about it, what happens is the hard part is getting to the end of the line, right? And a lot of times, you can actually go back and analyze that walk on the line and say, you know, if I start here, there's a certain chance that I'll get all the way out to the line, but it's more likely that I'll land back over here, right? Because I'm much closer to here, right? And in fact, it's sort of only a 1 over n chance that I get to this side of the line before I get back to this side of the line. Each time I land on this side of the line, I'm back in the clique world. And so I have all these distracting vertices. And it basically takes n time before I get out on the line again, right? So n time to get out of the line and n squared time, which was what we saw, only a 1 over n squared chance of getting to this line before you get pulled back into the clique. So that gives you an n cubed. About. Yeah? For not having the log. Oh, that's because we're working with expectations, right? The n log n for coupon collector is to cover all of the vertices, but now we're just trying to get out of the clique. That has a 1 over n chance of success every time. So, okay. All right. So these are 3 examples. I am out of time. So I guess what I will have to do is no, actually I need to give you, sorry, just thinking for a second. I think you can answer the homework without seeing the actual analysis. I think it's enough to know that the cover time for a graph is polynomial. Okay, so let me state for now that the cover time of any undirected graph is order mn. And I will have to prove that to you next time.
This is enough to do all the homework.
I believe that is the case. Okay. If it's not, I will double check, but if it's not, there might be one problem you have to work on Monday, but I don't think there is. Okay? I will see you on Monday. Yes?
Does the same result hold for directed graph?
Oh, great question. Okay, let me take 1 minute for that question. Do you think the same result holds for directed graphs? Yeah?
Directed graph connectivity is like NL complete. So like that would imply like L equals NL.
Yeah, so this is stuff that we're going to get into next time about what we've shown already by this claim is that you can solve undirected connectivity in log space, or what's in randomized log space, right? That's a complexity class. What he's mentioning is that directed connectivity is non-deterministic log space complete. So if you could solve it this way in log space, you would have a strong complexity result. And it is, in fact, not true that the cover time for a directed graph is polynomial. And you can construct a pretty simple example that has exponential cover time if the graph is directed. Which just goes to show you again that directed graphs are no fun, and everybody should study undirected graphs. Okay? I'll see you on Monday.